In this video, I will be telling you about the growth of functions, a concept that we would use to talk about the complexity of algorithms, namely the time complexity of algorithms, and particularly by expressing the number of instructions that are executed by a certain algorithm as a function um, of the input of that algorithm. Okay, so suppose you are writing an algorithm that is um, searching for a value inside a certain array. So clearly, that algorithm for search has a certain number of instructions. Typically, the core is a loop that is iterating over the n elements of the array. And clearly, if the size of the array is considered to be equal to n, then we can express the number of total number of instructions that are executed in terms of n, being a certain function of n. So typically you will find that the number of instructions would be a certain linear function of n, because you would be doing some b instructions inside the loop. So you will be doing those instructions n times, where once again n is the size of the array, plus maybe a few initialization at the beginning, and a few statements at the end to return the final value. Okay, so when it comes to sorting algorithms, as you may have noticed, we have typically nested loops. Okay, where the first one is almost to the order of n, and the second one it's almost to the order of n. And so repeating the same n statements, or sorry, statements n times, and then repeating the whole inner loop n times would give you something like a certain n square execution of certain instructions, and a certain n execution of certain instructions, such as the initialization of the variable of the inner loop, the incrementation of the variable of the outer loop, and so on and so forth, plus a few constant number of instructions. So with this approach, we would be able to actually compare algorithms, even if they are doing different things, okay, and talk about their time cost, and whether they are efficient or can be enhanced, and so on and so forth. Okay, and particularly for the same problem, if we can write another algorithm, let's say B sort, okay, an algorithm B for sorting arrays, with a certain runtime complexity, or a certain lower number of executed instructions, then we can say that eventually the algorithm B is kind of like better of the algorithm A. Okay, so we'll be able to compare algorithms dealing with the same type of problems, but also we can also compare algorithms that are solving different problems, and this is really nice. So why do we do this? Because we do not want to count on the exact running time in terms of milliseconds, seconds, or whatever, because this vary from one machine to the other. So we don't want to compare the runtime, especially that even the runtime depends on the input size. Okay, so it should be a function of the input size. So if here we are counting the number of instructions, we have just to multiply this total number by the time needed to execute one single instruction on that machine, and then we will get the runtime. Okay, so rather from the function we can calculate the runtime, whether it's on a mobile device with a tiny spec, limited spec, or on a desktop computer, or even a server, but not the inverse. So if it happens that we are not using a computer at all, zero processes are running on them, and we are running a certain program, maybe we will have the result within a fraction of a second. But if the computer is busy with another process having a higher priority, so maybe the effective runtime will be 1 minute because just that computer was lagging or was busy with another task. So again, we want to use a formalism that helps us actually in studying different types of algorithms for the same type of problems or for different problems, and that is independent of any machine architecture. Um, in general, in computer science, we want to understand how quickly an algorithm can solve a problem as the size of the input grows. We can compare the efficiency of two different algorithms for solving the same problem, and we can also determine whether it is practical to use a particular algorithm as the input grows. Um, so motivation for this, suppose that you're building an application to help in searching for books, research papers, and documentaries. So imagine that the total number of items here in this library database is equal to n. So we have n different items being books, research papers, and documentaries at the library. So you were able to write two different programs. Imagine one program called A and another called B, where the first one for that same number of items, library items, and is costing you 300 times n plus 8. So how could it be? It could be that A is having one single loop that is iterating over all the n elements. Okay, it's just one possibility. Okay, just imagining that we have 300 statements written or instructions written inside this loop, plus like few instructions at the beginning and the end, let's say 3 here and 5 there, okay? So in total, we would have 3 times n plus 8, okay? Uh, Suppose that you were able to write a different program that is costing 0.5 n squared minus 10, so kind of like having a nested loop, okay, but you are also having an if statement and you're executing n over 2 times this block of code, and you only have one instruction in it, but you are looping for n here, okay? So suppose here for when I is, let's say, divisible by 2, you're executing this code. So this code is executed n over 2, and the outer code is looping n times. So all in all, you will have n squared over 2. And suppose that you're also excluding 10 different statements for particular values. So anyway, this could be a fact that you have in hand, and now you are wondering whether the algorithm A or B are whether A is better than B or vice versa. So you have to consider actually large values of n, because up to a certain size of your library items, of your library database, you will see that the algorithm A would do better. Okay, so suppose your n is equal to 100, then FA of 100, if you have 100 books or items in the library, you would end up with something like 3 times 10 to the power 4. Okay. While on the other hand, FB of 100 would be half of 100 square, which is actually um, 10 times 10 to the power 4, actually, because it's 10 squared to the power 2. So you end up having 5 times 10 to the power 3, okay? So something like 5,000, while here you are having kind of um, uh, 30,000, okay? So until now, you can see that the algorithm B is doing much better because the runtime or the total number of instructions executed with B is much less than the total number of instructions that are executed with A. But if you plot the graphs of your two functions, you notice that starting from a certain threshold, it happens to be around 600 here, the function b would increase largely than a. Okay, um, and from that specific point, f of b dominates fb of n dominates fa of n, which means that the runtime of the algorithm um, uh, b would be much greater than the runtime of the algorithm a, given the same machine specifications if you run them on the same machine. So no matter what the machine that you choose, starting from that input size, this would be the case. And this is still actually a very reasonable threshold, because you can imagine that the database of AUB has already accumulated much more than those 600 different items. Okay, so even if you find that this number is large, but actually over time, if this was the number of items collected in a certain library database, we would have largely exceeded this number. Or if it was the number of students and your algorithms were searching in this set of students, or sorting that list of students by name or grade, then this will only increase over time. So this is why we are interested on the long run of the algorithms. Add to this the current trends, where we have uh, um, typically big data on the cloud and in our servers in general. We keep everything. We have many applications with very large volumes of data. So in this case, our algorithms will typically run on very large values of input or sizes of input. And this is why we are interested in knowing how the algorithms will do asymptotically when n becomes really big. Okay, not on this tiny chunk where n is still less than a certain finite small value. To do so, actually, to think about algorithms and to be able to compare them, we should understand three different notations that actually encompass actually, or encode the fact that one function dominates another, um, um, or that actually that two functions have the same order of growth almost. Okay, um, and with the notion of one function that dominates the other one, well, this one is dominated by the other. Okay, so we have a dual notation for these two facts. Sometimes we can just prove that this one is much slower than that one. Sometimes you can prove the inverse. So we have three different notations. One, it's called the big O notation. So here we can say that F2 is in the big O of F1 is dominated by F1. We can also say that F1 is a big omega of F2. Um, and actually, if F3 and F1, they have the same order of growth, then we can say that F1 is a big theta of F3, and vice versa. We can say that F3 is a big theta of F1. So it's a grosso modo the ideas, but we have certain technical details when it comes to the definition of each notation. And when it comes to proving that a certain function is big O of another one, or big omega or big theta of another one, then you have to stick to that formal definition so that you make no pitfalls during your proof. So today we will deal with big O, and then during the live session we will review the ideas presented here, and we will elaborate more on the big omega and big theta notations. Let's start with the big O. If you have two functions f and g, from the set of integers or the set of real numbers to the set of real numbers, we say that f of x is big O of g of x if there are constants c and k such that for every x that is strictly greater than k, f of x is less than or equal to some constant times g of x. Well, actually, um, the exact definition is with the absolute values of f of x and g of x. But since we are the x values that we are concerned with in our course and in algorithms in general is the input size. So since x represents the input size um, of a certain algorithm, it's typically x is typically greater than or equal to 0. Okay, so no one will ask you to search in a list of -5 books. Okay, so this cannot happen. Okay, and even the number of statements, so even the value of the functions f and g, h, whatever function we will talk about in this stack of slides, they will yield images in R plus because they represent the a number of instructions that are executed given a certain input size x. So this means that number of instruction is necessarily positive because it's impossible that you can solve a problem by executing -5 instructions, let's say. Okay, and it's really the case that it's 0. So at least you need to execute few instructions before solving any problem, no matter how tiny it is. Okay, even if there is one single formula, arithmetic formula that returns it, so at least you would have written that line of code to execute your program and solve your problem. Okay, so this is why we can confidently get rid of these absolute values from now on, but just for the formal definitions, we can keep on them at the beginning. So, and just to see this visually, to see this definition visually, so actually those two constants, C and K, represents two things. So K is kind of a threshold, um, starting from which the function f of x necessarily is dominated by g of x. Okay, so maybe before k, it happens that g is being dominated by f. Okay, but starting from k, so maybe a little bit before k, maybe exactly at k, uh, we don't know, but just a certain threshold, you have to designate a certain threshold after which you have a guarantee that g of x is dominating f of x. Actually, it's not necessarily to have g of x dominating f of x. It could be some constant times g of x, because maybe your function is g of x is going this way. So multiplying by this constant factor would help you to prove your point for smaller value of k. Okay, so maybe we have a better visual here. So once again, you have your g of x here, and multiplying it by a constant factor. Once again, c should not be a function of x, just a certain number, a fixed number, a finite number. Okay, would lift your curve a little bit and would help you to find a reasonable value k, starting from which for every x from now on, you would see that c times g of x is dominating f of x. Okay, good. So in this case, we would read this as f of x is big O of g of x, or is n big O of g of x, or g asymptotically dominates f. The constants c and k are called witnesses to the relationship of f of x and g of x. And it's only necessary to provide one pair of witnesses, although you can see on the next slide that once you can find a couple C and K, well, actually you can find an infinity of other C primes and K primes for which this property also holds. Actually, any pair C prime, K prime, where C prime is strictly greater than C and K prime is strictly greater than K, we also have this inequality. F of X would be found to be less than or equal to any other C prime that is greater than C, okay, times G of X. And this would be true for any k prime, for any x that is strictly greater than k prime, where k prime is also greater than k. Okay, so yeah, so there is an infinity of witnesses, practically, and infinitely many pairs of witnesses in practice. So um, an important point about the big O notation, it's wrong to write f of x equal to the big O of g of x, because big O of g of x is not a function, it's not a value. Okay, so instead we say that f of x is big O of g of x, or it is in the big O of g of x if we define the big O of g of x to be the set of functions that are asymptotically dominated by g of x. Okay, so um, okay, so uh, usually we will drop the absolute value, as I told you, because we deal with functions that take in positive values and return positive values too. Good. Let's consider one example first, and to check how can we prove that a certain function is to the big O of another one. Our first example is f of x equal to x squared plus 2x plus 1. I want to show that this is big O of x squared. So at the first sight, we would say that this function is always bigger than x squared when x is positive, okay, because we are adding stuff to it. But don't forget that it's sufficient to find a certain threshold k, after which, if we multiply this function x squared by a certain constant, sufficiently large constant, then we can actually have that constant times x squared exceeding the other function systematically, the other function that is, so it should not be linear, it's also quadratic, but it's a function where so x squared plus 2x plus 1, we can find a constant c sufficiently large to exceed systematically, starting from a certain threshold k, the function f of x being x squared plus 2x plus 1. So now technically how to prove this? So let's write once again clearly what we want to prove. We want to prove that there exists a k and a constant c such that for every x strictly greater than k, um, f of x, okay, is less than or equal to some constant times g of x. So I'm just recalling the definition. Um, so actually, there are two different ways or multiple ways to find those such pairs. Okay, one way of doing this is to um, measure each one of those terms by a certain constant times x squared. So for example, we know that x squared alone, the first term, is less than or equal than x squared. And we know that 2 times x is less than or equal to x times x for every x that is actually greater than or equal to 2. Okay. So this is practically for every x. And this one is for every x that is greater than or equal to 2. And we know that actually 1 is less than or equal to x squared whenever x is greater than or equal to 1. So now we can take this common range, which is for every x greater than or equal to 1. We will have this term plus that term plus that term less than or equal to those terms here. Okay. Okay, so we can take as a common denominator the x greater than or equal to 2 in this case. Or we can also replace this one by the fact that 2 times x is less than or equal to 2 times x squared for every x that is greater than or equal to 1 also, okay? So it's up to you. You pick up your ranges, and accordingly, or your k, and accordingly you will have different constants. So for example, in this case, for every x greater than or equal to 2, we will have um, x squared plus 2 times x plus 1 less than or equal to 3x squared, okay? And for every x greater than or equal to 1, um, we also have x squared plus 2x plus 1 less than or equal to 2x squared plus 1x squared plus 1x squared, which is 4x squared. Okay, so it's really up to you to find your K and C pairs as you wish. Okay, well, actually, I have to admit that the first method is the most common one. Okay, um, it doesn't require a lot of effort or tuning for the values of x. Just actually measure each term that you have here by the corresponding term with the highest uh, power, okay, and with the same coefficient. So you will end up having this term being measured by the sum of those coefficients multiplying the highest power. So I mean, if your polynomial is ax squared plus bx plus c, well, this you will find that this is less than or equal to a plus b plus c multiplying x squared, okay, for every x that is strictly greater than 1, okay? So double check it, because when x is strictly greater than 1, then c is less than or equal to c times x squared, and b times x is less than b times x squared, and ax squared is less than or equal to ax squared. So finally, this sum would be less than or equal to the sum of the coefficients times x squared. So finally, for every x greater than 1, you can have this major constant that is equal to the sum of the absolute values of the coefficients multiplying x squared. Okay, so you can find this obvious constant. We will see a generalized proof for any polynomial of degree n in a few slides. Um, Alternatively, we could tune the values and just have a lower bound here, a lower value for C, but with a relatively higher value for K. Okay, and this would be another witness for the domination of x squared over f of x. Okay, once again, you have a very visual presentation of this fact. Let's get back to some of the important points about the big O notation. So if both f of x is to the order of g of x and g of x is to the order of f of x, then the two functions, they are of the same order of magnitude. Okay, they have the same order or the same order of magnitude of growth. Um, um, really call it as you like. It just denotes this fact. If f of x is to the big O of g of x and h of x is larger than g of x for all positive real numbers, so it means that uh, h of x is actually dominating um, g of x. Well, in this case, clearly h of x dominates f of x. Okay, so because finally, when you are able to write this, then you will be able to write this at the end. Why? Because g of x is less than or equal to h of x for every x. Okay, just a proof of the usefulness of this lemma or fact is that when you are asked to prove that, for example, this function is to the big O of x cubed, or factorial of x, or 2 to the power x, or whatever you want. So any function that is systematically greater than this function for every x, I think this would be very useful. You just can take it for granted, okay? And even if you are asked to prove it for multiple functions, then just prove it for the smallest one, okay? And you will see, or like in this case, the smallest one is x squared. And then if you are able to do it, then subsequently, you will have it for granted for the other ones. For many applications, the goal is to select the smallest function, okay? That because it really gives you the best insight, okay? Um, so we want to talk about the tightest bound. Let's consider another example. Can we prove that 7x cubed is to the order of x squared? 7x squared, sorry, is to the order of x cubed. Well, actually, when 7 is strictly less than x, it means that x is strictly greater than 7. We have 7x squared strictly less than x cubed. Okay, so for k equal to 7, we can have c equal to 1, and actually for every x that is greater than 7, it happens that 7x squared is strictly less than um, uh, the constant x cubed. Okay, sorry, it's less than or equal to 1 times the function x cubed. So for c equal to 1 and k equal to 7, we can show that 7x squared is to the order of x cubed. I think you can notice that this also works for k equal to 1 and the constant c equal to 7. But is it always feasible to find those pairs? Well, actually, it's not, because, for example, you cannot show that n squared is to the order of n, okay? No way a quadratic function would be dominated by a linear function. Okay, no matter how further you push it with a constant, okay, no matter how you push this, the quadratic function would always exceed that linear function. And okay, so whether it's n or c2 times n or whatever you choose, you will see that your n squared function would always exceed it. Okay. And we have an elegant mathematical proof for this by contradiction. Suppose that there are constants c and k for which n squared is less than or equal to that constant c times n whenever n is strictly greater than k. Okay? Well, when you divide both parts of the inequalities by n, you divide n squared and n so suppose like even if k is equal to 0, so n in this case is strictly positive, so it cannot be 0, so we can divide both parts by n, and then we get that in this case n must be necessarily less than or equal to a certain constant c for all n that are greater than k. This is impossible. No. So even if you choose k reasonably to be lower than c, okay, well, actually, n is less than or equal to c only in this chunk, okay? So for all the n's that are greater than k but less than c, this holds. But for no matter what c is, you'll always be able to consider n's that are bigger than c. And in this case, uh, those ants do not actually fulfill this condition, okay? So it's not true that you can find such constants, okay, for the function n squared when compared to the function n, okay? So no way the linear function n would dominate the quadratic function n squared. Okay, but we can prove that for whatever polynomial, okay, that we have with a certain power of x, we can show that this is to the order of x of n, okay, x to the power n. It means that it's dominated by its highest factor, xn, okay? So we call it usually the leading terms, or okay, the leading factor in that polynomial, okay? It's the highest value in that polynomial, and it leads the growth of the function. So how it happens, how can we prove it for any polynomial where at least an is different than 0, okay? Because otherwise, uh, this would mean that if an is equal to 0 and an minus 1 is different than 0, then the polynomial, in fact, is to the power of n minus 1 and not to the power of n, okay? But whenever an is different than 0, no matter what you add here, whether some of them are 0 or not, those coefficients ai's, um, and no matter what an itself is, this polynomial can be shown to be can be proved to be to the order of x to the power n. And the proof goes as follows. Even if we keep the absolute values, we can use the triangle inequality property that you proved in one of the previous assignments. And then you just remove the absolute value to decompose your terms like here, and then you can divide by x to the power n. You will be left with this term an here plus an minus 1 over x, and then an minus 2 over x squared, and so on and so forth, down to a 0 over x to the power n. For k equal to 1, so for every value of x that is greater than 1, all those fractions, 1 over x, 1 over x to the power n minus 1, 1 over x to the power n, they are less than 1. Okay, so we can measure them. So we can show that this function here, this polynomial here, is less than or equal to x to the power n multiplied by the coefficients alone, okay, without them being multiplied by 1 over x to the power I, okay? So once again, because when x is strictly greater than 1, 1 over x is strictly less than 1, okay? So this means that a n minus 1, okay, times 1 over x is less than a n minus 1, okay? And we can do the same for all the other coefficients, ai's. So this is why we can replace those ai's multiplied by a certain degree of 1 over x by themselves, and then we can get finally to this form where the sum of the coefficients gives you a certain constant c that when multiplied by xn gives you a function that is majoring, that is dominating f of x, okay? So it's sufficient to consider the constant to be the sum of all those coefficients. And if you get few slides earlier, you would notice that we used this trick when we proved that x squared plus 2x plus 1 is less than 4x squared, okay, where 4 is equal to the sum of 1 plus 2 plus 1, okay, the sum of all the coefficients, and this is true for every x that is strictly greater than 1, okay? So the leading term in this case is an xn, and it dominates the growth of that polynomial. Good. Let's check the big O estimates for some important functions. So we can use the big O notation to estimate the sum of the first n positive integers. Why this is important? Because sometimes in your nested loops, okay, typically in sorting algorithms, when you take I from, let's say, from 1 to, let's say, n minus 1 or almost n, and then from j equal, let's say, I to n, okay? Because you don't want to reconsider the values that exist at the beginning of the array. You just want to compare every value with everything that follows it. So in this case, each time you would do a certain constant number of statements multiplied by maybe the first time it's n or n minus 1, the second time it's multiplied by n minus 1, the third time it's by n minus 2, okay? And you're doing all those instructions. The last time when I is equal to n minus 1, and you start with j equal to I up to n, you would be doing only n minus n plus 1 instructions, okay? So it means you will be doing only one instruction, okay? So as you notice, this is equal the total number of instructions, when you unfold both loops, you will find that it's not equal to n times n, but it's rather equal to n instructions plus n minus 1 instructions plus n minus 2 instruction plus 1 instruction at the end. Okay. Nevertheless, even if you have this summation, well, this would sum up to something to the order of n squared. Okay, so we will see this with the proof. So to show that the summation of the first n positive integers is to the big O of n squared, it's sufficient to apply this trick. So we can replace every term here by its by n. And this is true for actually for every n greater than 1, for k equal to 1. And in this case, the summation of all those n's is equal to n times the value of n, so which is n squared. Okay, and this is why we can confidently say that for k equal to 1, and for every n that is strictly greater than k, this summation 1 plus 2 plus up to n is less than or equal to 1 times n squared. We can also prove that when the function is the factorial function, then this is big O of n to the power n. Okay, it's dominated by n to the power n, and the same trick can be applied here. Actually, we can replace each term by n for every n greater than 1, and we will end up having this multiplication, which is the factorial of n, being less than the multiplication of n by itself n times, which is okay, so n times n times n times, which is actually n to the power n. And this is why we can confidently state this. Another couple of important functions. So we can estimate also the log of factorial of n now, because since we know that for c and k equal to 1, this is always true for every n greater than k. Well, actually, we can log both parts, and the log of n to the power n is equal to n times log of n. So this is why the log of factorial of n is less than or equal to the n times log of n. So it means that the function log of factorial of n is to the big O of n times log of n. Okay, these are really useful facts, and that you may use in other proofs of other functions. But it's an art actually to be able to sometimes to find the right way to prove that a certain function f of x is to the big O of g of x. Starting next session during the live, we will talk about the ordering of few functions. I highly recommend that you get a look at them, the typical functions that we often have to depict the runtime or the number of executed instructions in when we run a certain algorithm, and how they compare to each other. And then we will discuss a few rules about how to decide on the complexity or on the order of growth of summation of two functions, given the order of growth of each one of them or their multiplication too. And we will be doing this exercise together to discuss, to rearrange the functions that you have here with their respective order of growth. Okay, but the most important parts to come are to prove the big omega to show the to learn actually the big omega notation, and to see how we can prove such relations between functions, and to also talk about the big theta notation, and to see how we can prove certain properties on top of it. Thank you for your listening, and see you on Thursday.